Andreas. Okay, sorry. You're the next speaker, right? You're the following speaker? After this one. No. Please talk to. Okay, so welcome to this afternoon session. We have as our first speaker Robert Cameron, who will give a long-awaited talk about observational constraints on the Sun's global dynamo. So, Robert, go ahead.
Now? Okay, good. Okay, so I'm going to discuss the observational constraints on the Sun's global dynamo, and this is work with Manford and other people. This, of course, is the sunspot number, which we've all seen. Sunspot numbers come 11-year cycle, very different amplitudes from cycle to cycle, and we have magnetic observations, which I will discuss in detail for these cycles. So some large cycles, some small cycles, quite nice. So the observations we have, the magnetic observations, observations of the radial field coming out of the sun, and the toroidal field on the sun's surface. So this one Henna would have shown you on Monday. So this is latitude versus time, the axisymmetric component of the radial field. And this one is the axisymmetric component of the phi component of the field. So the azimuthal field as a function of time and latitude. And this one is not so often discussed in the dynamo literature, but it's very robust. So this is from two different instruments. This is from Wilcox Solar Observatory. This is from Mount Wilson Observatory. They've observed different times, but they give you the same answer for both components of the field. So this is what the field looks like. What is the azimuth for the averaged phi component of the field? So this is the toroidal field if you're from the planetary community or the stellar community. It's the m is equal to 0 component of the toroidal field. And it corresponds to flux emergence. So what we have here, the dots are sunspots or active regions. And as Henna mentioned on Monday, active regions involve dark features on the surface of the sun. Before the active regions begin, we have ephemeral regions. These are don't have enough flux to form a sunspot, but they emerge with the same east-west preference as the active regions, and these extend from much earlier and much longer. And what this color is showing us, what the toroidal field at the surface is showing us, is where the flux emergence is occurring, regardless of whether it's occurring in the form of spots or in the form of the ephemeral regions. It's weaker when there's only ephemeral regions, just because less flux is coming up. And both of these contribute to the solar dynamo. If you want to sort of understand what we're seeing the line of sight component of the field, and as flux emerges with some velocity u r prime, so a radial velocity, flux is carried up through the surface, through the photosphere, and we observe it whilst it's traveling through the photosphere. When we do simulations, we often approximate the photosphere above the photosphere with a potential field. If we do it with a potential field, then of course there's no phi component to the field. So this flux emergence is then just infinitely fast. However, because the density isn't 0, this loop rises at about 1 kilometer per second, and we can observe it. We can observe it, we do observe it, we've observed it for the last 40 years. This talk, I'm going to only have one equation, because as Steve said, this is where we're arguing in the solar community over the induction equation. And what I'm going to do is just apply Stokes Theorem, because it's easy to do. And basically what you're doing here is it's a conservation law. And we should see what happens to the conserved quantities, not only, for example, helicity, but also toroidal flux. Unlike the people in the geo community on the sun, this the microscopic diffusivity is tiny, 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 tiny. We can forget it. So this term, we don't have to worry about at all. It's not going to contribute to the surface integral. And because it's convenient, I'm going to introduce the large scale, so the axisymmetric fields and flows using brackets, and the non-axisymmetric components using the primes. The conclusions of my next part, we're going to have the flux generated by the differential rotation, and this will be the contribution coming from the axisymmetric U and the axisymmetric B, and I'll show you the observations imply it's about 5 to 8 times 10 to 23 Maxwells per cycle per hemisphere are generated. And this is the omega effect. What we generate, has to go somewhere. And it turns out most of it gets lost through flux emergence. So we generate toroidal field by winding up using differential rotation, and then it's going to pop out through the surface, and we lose about 3.3 times 10 to 23 Maxwells per cycle per hemisphere. So most of what we generate we'll lose. How to do this? Well, as I said, we've got Stokes Theorem, and this is the surface and the contour I choose to use. So when you do this, you're free to choose this A, and then the contour is just the edge of your area. So blah, blah. I begin looking at what happens in the interior. So I place this part of the contour beneath the convection zone. Because it's beneath the convection zone, sufficiently far beneath, then the 22-year cyclic component just will have no contribution whatsoever. You may have some skin depth. You place this beneath the skin depth, you'll have no 22-year cycle at that depth. I can, because of heliososmology, move into a coordinate system rotating at the rate of the equator. So here, if you look at heliososmology, we've seen this before. I won't explain it again, except for to say the color and the contours are of the rotation rate. So I can move, because the equator is rotating at an almost constant rate, I can move into a framework where this framework where the equator is not rotating. And then, along the axis and along the pole, the large-scale axisymmetric components of the velocity vanish. So in this framework, I then have gotten rid of the contributions from the equator, from the interior, and from along the axis. I'm only left with something from the surface. What I'm left with at the surface is somewhat ugly. It's the U cross B now evaluated at the photosphere, and it's going to be the terms which remain are the U coming from differential rotation and the radial component of the field. There's of course also a radial component of the velocity, but it vanishes at the surface, so we don't need to consider it. And this has a very nice advantage of being observable. We can observe the differential rotation at the surface. We can observe the radial field at the surface. I can multiply these two together, and I get the integrand, except for this factor of r squared, which is quite well known. And you can see the integrand is concentrated at the poles and has this form. I do numerical integration, so it's more or less easy enough, and I find 5 to 8 times 10 to the 23 Maxwells per hemisphere per cycle are generated. When I want to look at the toroidal flux loss, I'm now going to be concentrating on this U prime and B prime components. There will be diffusive losses for all of these segments, but because of symmetries, they'll just be diffusive losses. And something's going to happen at the photosphere, and at least we can estimate or calculate how much is lost through the photosphere, because it's going to be coming from flux emergence. And remember, we have this B phi, which is due to flux emergence, this average toroidal field coming from flux emergence. And the observers, so the solar physicists who like this type of model, have actually measured the velocity at which the flux emerges. And it's about radial velocities of 1 kilometers per second. So I'm going to measure just after or during the process of flux emergence how much flux is lost. Of course, you may say, and people in the 80s did, Parker, for example, all these field lines retract back. So we have an emergence, the loop rises up, but then over a course of days or weeks, most of the flux retracts back beneath the surface. And therefore, what we emerged through the surface heals, and we don't actually lose any flux. This turns out not to be consistent with what we observe. So we do observe most of the flux going back beneath the surface. More than 99% of the flux will retract back beneath the surface. But whilst it's retracting, some small fraction of it is moving further and further apart. It moves further and further apart because of the random supergranular motions. Move some of it together, move some of it apart. And what you find, if you do the maths properly, is that the amount you lose during the initial emergence is conserved. At all later times, the same amount of flux is sitting above the surface. So remember, the amount of what we're talking about, or what we're interested in, is not the flux of this emergence. It's how much of the subsurface toroidal flux we've lost. And this is given by this formula. So it's a flux in the loop above the surface. So here the flux is decreased by a factor of 5 compared to initially. But the length, the separation, has increased by a factor of 5. And therefore the mean, which is the product of the flux times the length divided by the circumference of your star at the latitude, is constant. So with this in mind, it becomes completely trivial to calculate how much we've lost for the photosphere. We've lost from this component, where it's u phi times b. We look at the theta component, these two, and the one we're going to look at first will be this one. And in this analysis, this is the one which dominates. It's radial field carrying up a phi component of the magnetic field. This happens in small patches where flux emergence occurs. The velocities are 1 kilometer per second. Typical field strengths here will be 300 Gauss. This is basically equipartition with the kinetic energy of the convection of the surface, but this is just observed. And the important point is when you take the spatial average, you're going to get 1 kilometer per second times the average field strength we see up here. And this is about 0.2 Gauss. So then this integral becomes the emergence times, there should be in brackets here, the average field strength of which is 0.2 Gauss times pi on 2r just for the DL. You can do this and you get 3.8 times 10 to the 23 Maxwells per hemisphere per cycle. Alternatively, perhaps you think, oh, this measurement of the toroidal field is nonsense, where people have, Bieber and Rast used in situ measurements from near the Earth, spacecraft measurements, and looked at the difference between the inclination of the velocity in the magnetic field and in the solar wind, and they infer we lose 5 times 10 to the 23 Maxwells per hemisphere per cycle. So this comes from in situ measurements. Alternatively, because we've got multiple ways of looking at flux emergence, you can use these results from Kay and Harvey. If you use those, you get about 3.3 times 10 to the 23 Maxwells. So this is really, however you look at it, we're losing 3 to 5 times 10 to the 23 Maxwells per hemisphere per cycle. So we generate this, we lose this. Okay, and what's more, if we generate more toroidal field, we lose more. And that's shown in this plot by Wang and Sheely. So here they compare the minimum AA index. So this is a geomagnetic measurement of essentially fluctuations in the magnetic field of the Earth. The variations, and they measure the strength of the next cycle. So you measure this at minimum, and it turns out, you can look at Wang and Sheely, so this is a measure of the polar fields. And as we've seen, the polar fields are what goes into the integrand. So the polar fields are strongly correlated with the amplitude of the next cycle. So you generate more toward the field, and then you lose more half a cycle later. Next, I want to briefly discuss where the polar fields come from. So the polar fields are critical. Where do they come from? Actually, I'm not going to answer that question. I'm going to answer the question of how they change from this time to this time. Because this is a much easier question than working on what happens in between, because at these times, most of the flux, essentially all the flux, is concentrated at the poles. So my question now becomes, how does the net radial field in each hemisphere change from time 1 to time 2? How does this go from being blue to red? And this is a change in the net polar field. And because it's a change in the net polar field, I can use Stokes Theorem again. Now my surface will be the whole of the northern hemisphere. My contour will be the equator at the photosphere. And because my contour is the equator at the photosphere, this is, of course, observable. So there were two terms. There's this URB theta. So this corresponds to flux emergence across the equator. And yeah, we see flux emergence across the equator. Here's an example. Ba-boom, ba-boom, ba-boom. This is a large amount of flux which has emerged just across the equator. It was easy to find because it's huge. The other term you have comes from this term, the theta component of the velocity carrying across radial field. And this is essentially the random walk of the supergranules. So the supergranules we've heard before, they're a convective velocity pattern, more or less randomly organized. And they advect the magnetic field in random directions away from the center of the supergranules. And some of this carries flux across the equator. And this one has a systematic component because the BR has a systematic component. So here we can see close to the equator, there's more blue flux in the northern hemisphere and more red flux in the southern hemisphere. And this will lead to the advection of red flux to this hemisphere, reversing the polarity, and blue flux to this hemisphere, eventually reversing and maintaining the polar fields. So if you just look at the active regions, and it turns out the rate of emergence of ephemeral regions in active regions is such that this is dominated, particularly in the noise, by the active regions and not smaller ephemeral regions. So if you just include the active regions and you use the observed tilts, well, the black line is the axial dipole moment, which is closely related to the net flux in the hemisphere, which is observed from a tilt space mission. And this is what you get if you integrate this equation in time using the observed properties of active regions, of individual active regions observed during this cycle. And it matches very well. If you don't include the actual observations of the tilt angles, so all the properties of the observed active regions, you get the wrong answer. That's not surprising. You do use the observed properties of the active regions, you basically get the correct answer. And this is essentially showing you that Joyce's law and the fluctuations in Joyce's law are important. Joyce's law is this tilt, and the tilt is what Hannah explained, that the leading polarities of active regions tends to emerge slightly closer to the equator than the following polarities. So if I go back, this is blue because of Joyce's law. So in this case, the blue ones emerge slightly closer to the equator, the red ones emerge slightly closer to the poles, and therefore this becomes blue and this becomes red. And then because it's blue, easier to get stuff across the equator. So this is Joyce's law, and this is an image from one of Hannah's papers. And you can see Joyce's law, very, very weak. This is almost east-west aligned. It's a slight difference from east-west alignment, which gives rise to the systematic component of the solar dynamo. It's not a strong thing. Its exact cause of this is unknown. It's clearly the Coriolis force, but it could be Coriolis force acting on convective flows, flows associated with the buoyant rise tubes, some other flows, we don't know. However, we observe this, and this is sufficient. Of course, it's extremely noisy, which is why some cycles have strong amplitudes, some cycles have weak amplitudes. So I'll come to my conclusions for the first part. Flux emergence removes 3.3 times 10 to the 23 Maxwells per cycle per hemisphere. Slightly more is generated using by differential rotation, and the only way of generating the net flux is through magnetic field, which threads through the surface. If you don't have magnetic field threading through the surface, you don't generate net toroidal field, and therefore you cannot lose it. The net flux of the threading through the surface at the end of the cycle ends up at the poles. How much depends upon how much is across the equator. So the solar cycle involves the net toroidal field in each hemisphere, and the surface plays a crucial role. I just briefly want to mention now the Babcock-Leighton dynamo and how it fits in with this. So here we have the same thing, the generation and the loss. So the generation is caused of the toroidal field, is caused by the winding up of the polar fields. So the field multiplied with differential rotation gives you this axis, and here we lose flux through the surface. And we saw a poloidal field budget, which is we have emergence that's close to the equator, some flux gets across the equator, at the end of the cycle ends up at the poles. So we generate toroidal field by flux emergence, tilted flux emergence, and we have a poloidal flux at the end of the cycle. What we need, however, is some motion of where the field is stored. So the poloidal field, I told you that what happens in the equator is critical. You have to get flux across the equator. However, where it's important for the generating toroidal field and where we observe it to go is to the poles. So you need to transport it from here, from the equator to the poles. And similarly, if you think the toroidal, the latitudinal differential rotation is important, then we generate the field at 55 degrees latitude, but we have to move it to latitudes of 35 to 5 degrees where it emerges. And we need to move almost all of it. This one we have observed. This one is consistent with the helioseismically inferred return flow. However, we've got no real way of knowing if this is meridional flow, if it's a dynamo wave transport, or if it's turbulent velocities. However, there needs to be something which looks like a velocity which moves it. We also need to, if we want to have a dynamo loop, we need to assume something about flux emergence. And the easiest thing to assume is that the flux which emerges is related, and I'll assume it's linearly related to the toroidal field density. And if you assume this, you then have enough to have a dynamo model. This is the Babcock-Leighton dynamo. You can compare the observations with the model eigenfunctions. So the surface radial field is common to both of them. The surface toroidal field only really exists in the observations. In the simulations, the equivalent for the 1D Babcock-Leighton model is a radial integral of the subsurface toroidal field. And that was my talk. Questions?
Yes, questions.
Comments? Chris.
Chris.
Thanks, Robert. Very interesting talk. You don't really have any role for the diffusion, turbulent diffusion of toroidal flux. Is that right? In your budget, yeah. Essentially, what you're saying is that what is generated by the omega effect is all lost essentially by coming out through the top.
Yeah, but I'm certainly not ruling out that this flux emergence is related to turbulent diffusion. I don't know what turbulent diffusion looks like,
No.
and the value for this, for the escape. So basically you have to have all the flux escapes on a time scale of 11 years, or most of it escapes on a time scale of 11 years. And if you take the depth of the convection zone and a diffusivity of about 100 kilometers squared per second, which is what people who do the simulations think it is, then you lose on this timescale of 11 years.
Yeah.
So
I mean,
flux
the fact that your generation and your stuff coming out is roughly in balance suggests that it's probably only a minor role, doesn't it?
Or the flux emergence is somehow the equivalent of turbulent diffusion.
Yeah, okay.
Yeah.
Thanks.
I don't know how to relate the mean field concept of turbulent diffusion to observed to observations.
So I mean, this is a very different picture from sort of Parker's alpha omega dynamo waves, isn't it? Where the diffusion.
This is the Babcock-Leighton, which is the one solar physicists like, and we like it because it's large aspects of it are implied. The role of the surface field has to be there because it produces a relevant amount of flux. It produces what we see, and not only it produces what we see, but the variations in the amount it produces, we see as variations in the amount which emerge.
Yeah, thanks.
Sasha?
Robert, I want to go back to what you showed for the Joyce law, where you were seeing only a 2 degree, but with only 2 degree, when you do the horizontal average, can you really get...
So this isn't 2 degrees, this is 2 days.
2
this
days,
is the time after
but you
emergence,
said
so
they
this
were a
is what
very
it's
small tilt.
So the tilt is
Between
7
10 and-
degrees. It is small, but there's a large number of regions. This is why Henner said, and I remember clearly, Joyce law is a statistical effect. If you look at individual ones, you won't see it. You have to look at a huge number before it becomes apparent. And this is why some cycles are weak and some are strong. It just depends how much goes across the equator. If you end up unlucky with 5, 10 active regions, you don't get enough across the equator. I should also point out the total amount you get across the equator is about equivalent to one large active region. You have one large active region which emerges close to the equator with highly tilted, and you're finished.
Yes, what you got the ROGS one. Yeah.
Yes.
But I mean, it's how important in your model is the statistical average tilt angle?
So it's not my model where it's important. It's in this integral of you need to get stuff across the equator. Stokes Theorem tells you the only way to have a polar field is to get stuff across the equator. This isn't my model. This is Stokes Theorem.
No, that I understand. No, when you do the azimuthal average, what you are seeing, at one point you were showing the blue part and the red part when you were speaking of T1 and T2. Then this angle plays a key role in getting your dynamo.
Yes, so Stokes Theorem tells you that this little difference is extremely important for the dynamo. And this is why we put in considerable effort, not me, but Hannah, into determining what causes Joyce law. But it's critical for getting the flux across the equator. And getting flux across the equator is critical for the amount of field to get to the poles. It's the only way to get it there. And the amount of the poles is critical for producing the toroidal field on the inside, which is then what we see emerge.
Thank you. So we have one more question. Maybe Andreas can already start preparing.
Hey, I think I already asked this question a few years ago, and you might have answered, but I'm still worried about the integral going down on the sides. So there's one integral.
So you will have,
from the surface.
You certainly can, and I assume you will have, at late in the cycle, the flux gets generated, and you'll get some diffusive term across here. But because so we're talking, I guess, about the U prime and the B prime, the small fluctuating components, yeah?
Right. Well, won't both of them be there?
I've moved into a framework where this is 0. I rotate with the rotation rate of the sun, of the equator. Therefore, the large scale U phi is equal to 0. A large scale U theta would correspond to a cross equator would flow, which from symmetry grounds you expect to be small. It may have a small some impact, but it's small. It's random. And you don't expect it, for example, on ensemble averages. So I move into a system rotating at the rate of the equator, which I can do because the rate of rotation at the equator is independent of depth. And this gets rid of my u phi. You get rid of the u theta just by symmetry. You don't expect to have a flow going across the equator. The ur certainly will be there, but the ur has no contribution to this integral.
But isn't that, it's the turbulent EMF. I mean, why, right?
So the turbulent EMF are these ones, yeah?
Yeah.
Okay. So here, this is the symmetries of the equator are sufficient so the only term you get left is when you have a asymmetry between the field in this hemisphere and this hemisphere, so you have a gradient, so it's a diffusive term. But we can discuss it more offline.
Okay, I think we should move on, and let's thank Robert again.